వస్తాయా అవతలకోండి. నెట్ కనెక్షన్ చూడిపోవా, ఎందుకో స్లో అవుతుంది, స్క్రీన్ బ్లాంక్ ఉంది. నెట్ కనెక్షన్ ఒకసారి సార్ చూసినా ఒకసారి సెట్. అవునవును, నేను షేర్ చేసినా ఎందుకో రావట్లేదు, చూస్తున్నా. ఓకే, కనెక్షనా? ఓకే, సరే సరే, నేను చూస్తాను ఒకసారి. ఓకే, సార్ అదే వైట్దే పెట్టినా నేను.
స్టార్ట్ చేయట్లేదా?
మరి మీరు ఆ లైవ్ ఇస్తే స్టార్ట్ చేస్తారు.
ఇచ్చేసిన ఇందాక.
గుడ్ మార్నింగ్ డియర్ స్టూడెంట్స్. Very good morning, one and all. Here we are as the continuation of our previous class. Now we are dealing with the chapter of nuclei. Yeah. So yesterday we have studied we have discussed about the basic concepts of nuclei and also binding energy, types of nuclei, that is isotopes, isotones, isobars, isomers. Okay, and binding energy curve also we have discussed, and what actually the binding energy curve is giving information also we have studied. Now come to the next session, that is forces inside a nucleus. So what are the forces are inside the nucleus? Okay, so the forces inside the nucleus actually we can classify into four types, that is nuclear forces, that is coulomb forces, then tensor forces, and then hardcore repulsive forces. Okay, so now we will discuss about each of the topic now, that is first coulomb force. Okay, coulomb force, actually what is the coulomb force? As we have discussed in previous lessons, previous classes, the coulomb force is nothing but it is an electrostatic force of a repulsion or attraction. Okay, but here we are studying it is a electrostatic force of a repulsion between a proton and another proton. because I am discussing in case of nuclei, that is nucleus. That is the reason I am defining this the coulomb force like this. It is the electrostatic force of a repulsion between a proton and other proton. So between two positive carriers, that the force exerting is known as actually the coulomb force. These forces are responsible for instability of the nuclei. Okay, as the atomic number increases, coulomb force is also increases. Atomic number is nothing but what? Number of protons. If number of protons are increasing, the coulomb repulsive force is also increasing. Actually, the stability. Hence, why? Because the coulomb repulsion as keep on repulsion increases, the stability of a nuclei decreases. Okay, the stability of a nucleus decreases. Okay, now for example, the binding energy. Here I have given example the binding energy formula. The nuclear forces. Next, that is a coulomb force, which we have discussed just now. Come to now nuclear forces. The nuclear, the forces, yeah, the forces which are acting within the nucleus are among the nucleons are called nuclear forces. Nucleons are nothing but protons and neutrons, right? So the forces which are acting within the nucleus or among the nucleons are called nuclear forces. The nuclear force is much stronger than coulomb force. Remember, the nuclear force is much stronger than the coulomb force or the gravitational force also. In the chapter, in the first chapter in intermediate first year, we have studied various types of forces, right? Okay, there we have studied that is electrostatic force, nuclear force, coulomb force, gravitational force, like that we have studied. Here, the nuclear force is the strongest force. Okay, nuclear force is the strongest force among coulomb and gravitational force. Now I am giving here, see, a graphical representation here. That is the equilibrium separation on x-axis. The energy is on y-axis. When equilibrium separation is on x-axis, yet r naught, actually see, you are observing the curve is possessing like this, where r naught is the r equal to r naught is the equilibrium position. When r equal to r naught, the potential energy is minimum. Beta, potential energy, see, when r equal to r naught, what happens? Potential energy is minimum, that is at zero case. So whenever the potential energy is minimum, there the bond formation, that is actually the equilibrium position. Yes, see, point of inflection. Point of inflection means whenever the curve is redirecting. Redirecting means the direction of a curve, the point where the direction of a curve changes, that is actually the point of inflection. Okay, yeah. Now, the nuclear force between two nucleons fall rapidly to zero as their distance is more than femtometers. Femtometer means 10 power minus 15. This leads the saturation of forces. The nuclear forces are saturating forces. Okay, the nuclear force whenever actually between the two nucleons falls rapidly to zero, then what happens? The distance is more than the femtometers then. So this leads to saturation. Okay, the feeling of enough. Saturation means the feeling of enough. Okay, the potential energy between two nucleons as a function of distance, and it is minimum yet r equal to r naught. That's what I said just now. R equal to R naught means that is the equilibrium minimum position existing potential energy. That is the minimum potential energy existing point. Okay. Yeah. Now, the repulsive force between protons is about 10 power 36 times as great as the gravitational force between them. See, to the gravitational force, the repulsive force, that is to the gravitational force, actually, this is about 10 power 36 times. Okay, the ratio I have given, see, the ratio of a relative strength of a gravitational force, electrical and nuclear forces. See, let us suppose that if gravitational force is one amount, then the ratio would be, the electrostatic force would be 10 power 36 times to that, and nuclear force is 10 power 38 times. Is it okay? Properties of nuclear force. So what may be the properties of nuclear force? See, these are very strong and attractive forces. Okay, strongest force in nature. These nuclear forces are charge independent, because the force existing between proton and proton, neutron and neutron, proton and neutron, like that. Okay, these are the short ranged force. Short ranged force means the nuclear forces are applicable when the separation is very less, which is in the order of 10 power minus 15 meters only. It is strongest but short range. Okay. Yes, and these nuclear forces are spin dependent forces. Okay, that is spin dependent means nuclear force is the strongest as the spin of the nucleus is parallel. That is the spin means actually we have you people studied in the chapter of chemistry, the first chapter, where the alignment, the electron find the most probability alignment is the spin. Okay, and non-central, actually the nuclear forces are non-central. IPE point of view, very very important. What are the properties of nuclear force? Nuclear force are very strongest force. These are the charge independent, short ranged, spin dependent and non-central. Non-central means here the nuclear force does not act along the line joining where we have discussed in a coulomb's law. Coulomb's law, actually what we have from first center to, that is a carrier's first center to second center, we have drawn a line, and we took that line distance separation is r. That is actually that is what, that is a central force, where the this is the nuclear force is non-central force. It doesn't act on only a line joining through them. Okay, line joining to the particle. Okay, it is a field force actually. Yeah, the properties of nuclear force, again continuing, this is non-electrical force. The nuclear force is the non-electrical force and a non-gravitational force also. Okay, the exchange force, this is actually the exchange force means what we can say exchange force means. For example, if one neutron is splitting, so one neutron whenever you are splitting it can splits in the form of one proton plus one electron, like that here. Don't think that only the electron and proton here. Sometimes actually the minor particles, see I will explain you, like particles like mesons. Meson means we can represent like pi. Okay, nuclear force is due to the exchange of, exactly saying this is a exchange of pi mesons between the nuclear. Meson means it is a particle beta. Okay, mesons are the particles where we can represent that is a pi naught meson. Pi 1 meson is also there. Two types of, again where in the not only whatever we are studying electrons, protons, not only these two particles but also many nuclear particles we can we have actually, that is a mesons, what positrons. Actually the positive electron is nothing but positron, like that many particles are there. Okay, small amount of particles are there. Okay, pi meson, just I'm pi meson, about pi meson, actually the scientist Yukawa has predicted. How is according to Yukawa, scientist name beta, that is according to Yukawa, what he said means whenever a proton splits, see like this, whenever a proton, this is actually a reversible process. Okay, that is when a proton splits into neutron plus pi plus meson, it can split into neutron plus pi plus meson, and reverse, one neutron plus pi plus meson gives you one proton. like that. One neutron, see here, neutron means a neutral charge. Remember like this. Neutron means neutral charge. Pi plus. These, whenever this neutron interacts with positive meson, then it will give you proton. And the neutron, the neutral charge, whenever it interacts with pi minus, that is a negative meson, then it will give you, sorry, here it is electron beta. Okay, so this is actually the what we can say, um, proton plus neutron pi meson. So this is actually the reaction, according to Yukawa, this is the scenario. Okay, and see here we can write neutron only, that is okay. Now we are not speaking about that positron particles. Okay, okay, beta, clear. Slide, whatever the slide has, that clear only. Okay, the proton, which is again, whenever the in reversible scenario, the pi naught, neutron plus pi naught, neutron, that is neutron plus pi naught. This is actually according to Yukawa theory. Just this is, if you don't understand this, just leave it. Okay, why? Because this is just depth knowledge plus only. But you remember the point is that, it is a exchange force. Okay, yeah. And the nuclear forces show the property of saturation. They show, nuclear force shows the property of saturation. Okay, a nucleon does not interact with all other nucleons, but only with a limited number of them which are nearest to it. Okay, a nucleon does not interact with all other nucleons, beta, but only with a limited number of them which are nearest to it. And a hardcore repulsive force. The next force is hardcore repulsive force. That is the fourth type of force we are discussing. Okay, so here, if the distance between two nucleons become less than 0.5 femtometers, if the distance between two nucleons become less than 0.5 fm, there exists a force of repulsion. There exists a force of repulsion instead of attraction. These forces are called hardcore repulsive forces. They are strong repulsive forces. Actually, the hardcore forces are strong repulsive forces. These forces, yes, these forces keep the volume. These forces keep the volume and the density of the nucleus constant. Okay, tensor forces. Next, come to the tensor forces. Okay, the tensor forces means here all the nucleons have spin, so they behave as a magnet dipoles. There exists a force between two dipoles. This force is called tensor force. Okay, all the nucleons have spin, no, so they behave like a magnetic dipoles. There exists a force between two dipoles. The force exertion between two dipoles is called actually the tensor force. Okay, it is the tensor force is an attractive force. It prevails up to a distance of 3 femtometers. Okay, yeah, the tensor forces arises due to the spin motion of nucleons. Okay, now actually beta decay explains this tensor force very clearly. Beta decay is mainly due to tensor force only. Any nuclear reaction involves the conservation of mass, energy, charge, mass number, linear momentum, angular momentum. That is actually the tensor force. Okay, about it involves actually the nuclear reaction which involves mass. Whenever the nuclear reaction takes place, if there is a exchange, if there is a variation in the mass, energy, charge, mass number, linear momentum, like this all the quantities, then that is actually the tensor force. Okay, yeah. Now just remember the point and just keep attention, please. Which of the following is not correct about the nuclear forces? Tell me. They are short range attractive forces. They are independent of charge. They charge actually. They change to repulsive at very close distance. They obey universal square law. Tell me which is the answer. Remember that nuclear forces actually never obeys universal square law. Okay. Yeah. Nuclear forces between two protons and a proton and a neutron between two neutrons are respectively, how the relation would be? Tell me how the relation would be. Don't think that if proton proton means repulsion is more, neutron proton means less, like that. Actually, all are equal. Okay, the force exerting between all the particles in case of a nucleus is equal. Okay, now come to the next topic, the radioactivity. Okay, yeah, the radioactivity, the energy. First of all, we will discuss energy released in a nuclear reaction. Then we will shift to the radioactivity. Okay, the energy released in a nuclear reaction, whenever the nuclear reaction is taking place, how much the energy is, that is what actually we have studied according to that is energy, the energy, the mass energy conversation. Okay, that is Einstein relation. Q is equal to del mc square joules if del m is in kgs. Okay, so del m is what is delta m? Delta m is mass defect in nuclear reaction. Mass defect means already we have studied, that is if it is actually in million electron volt, we can study del m into 931.5 million electron volts if del m is in AMU. Now what I am writing here, see, delta m, which is that is mass of the reactants, is almost all mass of the products. Okay, that is mass of the reactants is almost all the mass of the products. Okay, means there is a difference, almost all equal only, but there is a small amount of difference. That small amount of difference only I am saying mass defect, that is delta m. Okay, so that amount of a difference between the mass of the reactants and mass of the products, that is actually the uh, delta m. Okay, yeah, if mr, let us suppose that if mass of the reactant is more, if actually mass of the reactant is more than the mass of the products, then actually energy releases is more. Why? Because reactants mass is more, no? Reactant mass is more means actually their release energy, the energy which is released is more. So actually whenever it releases, the energy released is more, actually we can say this is actually exothermic, it leads to exothermic reaction. Yes, the reaction is exothermic reaction. Which releases more energy is exothermic, which requires more energy is endothermic. Okay, yeah, according to chemistry, I think exothermic and endothermic. Okay, yeah, for example, if mass of the reactants is less than the mass of the products, then actually their energy would be absorbed. That is a required beta. If energy release, that is exothermic. Energy absorbed, that is a required. Energy required means this reaction we can say endothermic reaction. Okay. Now, example of exothermic reactions are nuclear fission and fusion. Remember, example for exothermic reactions are, because whenever the process of a fission and a fusion takes place, then what happens, in case of these two process, actually energy will be released. Okay, example for endothermic reactions, that is, let us I am giving here, where it requires heat. Actually whatever you are nitrogen with alpha particle which is equal to oxygen, hydrogen will be released, this section. This type of a reaction, actually the endothermic reaction, it actually it absorbs the heat energy. Okay. In exothermic reaction, the total binding energy of a products will be greater than the total binding energy of reactants. This is the point where you have to make underline. Okay. Exothermic, endothermic, we can classify, no doubt in it. If that is, if it is the reaction is exothermic, then the total binding energy of products will be greater than total binding energy of reactants. Okay. In endothermic reaction, the total binding energy of products will be less than total binding energy of reactants. Okay. This is what you have to remember. In terms of binding energy, the energy released in a nuclear reactions is given by, that is, the Q is equal to binding energy of products minus binding energy of reactants. This is what the main session which we are concluding here. Okay. Yeah, the topic. Yeah. Now that is radioactivity. Now we are entering into the that is topic radioactivity, actual topic radioactivity. What is radioactivity? See, the nuclei having large mass number are highly unstable and disintegrate spontaneously. Disintegration means with the time it is getting decay. Okay, the disintegrate spontaneously by emission of a radiation. Radiation means what? The emission of alpha particles, beta particles, and gamma particles. This is called natural radioactivity. Yes. So, what is radioactivity? The nuclei having large mass number are highly unstable and disintegrate spontaneously by emission of radiation. Okay, radiation is nothing but alpha, beta, and gamma radiations. Yeah, when a nucleus decays, it can emit particles or photons. Photon, not protons, but photons. Okay, which is a packet of energy which we have studied earlier. Okay, the decay products were originally called alpha, beta, and gamma. Decay products we can call it as alpha particle, beta particle, and a gamma particle. Okay, generally all are called radiation only, even though only gamma is actually a form of electromagnetic radiation. Gamma rays means actually we can take it as electromagnetic radiation. Okay, the radioactive law, what is actually on which law, we are based on which law this disintegration takes place. Okay, so radio, we are here to study about the radioactivity law. Very, very important. Be concentrate. Rate of disintegration of atoms at any instant is directly proportional to number of atoms present at that instant. How many number of atoms are there? That much disintegration can take place. Simple, no? Yeah. So that rate of disintegration means in activity. Activity means what? The disintegration, decaying. Activity means decaying. That is activity. That is number of disintegrations per unit time. That is the modulus of dn by dt means total number of dn by dt. D by dt of n. That is how many number of disintegrations are going on. Okay, within unit time. So that is d by dt of n means that is a lambda n. Okay. Yeah, where n is the total, actually the nucleus size, that is total number of nuclei. Lambda is the decay constant, lambda disintegration constant we can say here. Okay, so lambda is a disintegration constant which depends on actually nature of element. Okay, the disintegration constant can depends on nature of the element. Yeah, so n is the number of moles, then we can write it as, see, using Avogadro number, number of moles in n, how can we write it? That is a number of nucleons, number of nucleus size actually. Okay, nuclear number of nucleons, number of moles into n into a, that is m by n. Number of moles means weight in grams by molecular weight into Avogadro number. So that is unit for lambda. How we can write unit for lambda is nothing but it is second universe. That is a disintegration constant. Units are second universe. If nt, now I am giving you an equation. See, if nt is the number of atoms at any instant t, n naught is the number of atoms at t is equal to 0. Why? Because these are getting disintegration within the time, no? Let us suppose that nt number of n number of nucleons are there. After time t, you are getting the other number. That is, I am taking first nt number of atoms are there. Next, after time t, those will become n naught at time 0. Let us suppose that. So this is, and then we can write here nt is equal to n naught into n naught means actually the how much the here nt means number of atoms. How many number of atoms are there? N naught, that is the atoms at a time is equal to 0, and exponentially there is a disintegration is taking place. The meaning is that exponentially disintegration takes place. So e power minus lambda t. This is the equation. And from law of decay law, this is the decay law. Why? Because we studied how many number of particles are there within the time. Disintegration law this is. So dn by dt is equal to minus lambda n. Okay, so dn by n, if you write dn by n, what we can, this n will comes here, dt will be right side. Dn by n is equal to minus lambda dt. Minus lambda dt, now minus sign actually, why minus actually here? Minus indicating there is a disintegration, decreasing, no? From the initial session, the number of nucleons are getting decrement. Okay, so yeah, now I'm integrating here this dn by n minus lambda t. Okay, by taking such limits, integration by how I want to note the total number of total, that is small amount I have taken, no total. So initial state n naught to the nt. Okay, nt n naught to nt. I am, this is at a time t is equal to 0, n naught, no number of one at a time equal to t nt. So dn by n is equal to minus 0 to t, that is lambda dt. I am making integration here, that is 1 by n integration is log n. Okay, log n, 1 by n integral of 1 by x, that is 1 log x formula. Using that formula, log n naught, the limits right side, where minus lambda t dt, integral dt is t, lambda is constant. So I have taken out lambda, then t, and limits 0 to t. Yeah, now log, that is n ln I have written. So and to convert log again I have to multiply by 2.303. Yeah, ln n naught minus log nt, I am applying limits beta here. Yeah, in this equation I am applying limits ln nt minus ln n naught, which is equal to minus lambda t minus 0. Yeah, now I am taking the same right side. Yeah, ln nt by n naught, which is equal to minus lambda t. Now nt by n naught, which is equal to, see, I'm converting this ln, I'm taking into right side, then it will be e power nt by n naught, which is equal to e power minus lambda t. So n naught by nt e power lambda t, making ulta to avoid this minus. Okay, nt is equal to n naught into e power minus lambda t. This is the proof. Okay, nt is equal to n naught into e power minus lambda t. Is it clear? Is it clear, dear students? This is the proof for the law of disintegration. That is, what is the law of disintegration? Nt is equal to n naught into e power minus lambda t. How we have concluded this? This is the final equation. Okay. Yeah, you practice with pen and paper. Okay, don't just don't leave by watching. It is not a movie, no. You have to practice everything. Moreover, the physics you have to understand, you have to practice, and you have to keep it in mind. Okay. Okay. Yeah, activity. Activity, and what is activity? We are observing radioactivity. Radioactivity is nothing but what? Decaying rate. That is, decaying rate means a disintegration is the activity we are observing here. Okay, so disintegration, see the disintegration, this is actually the main formula of disintegration, that is dn by dt, that is the nuclei is getting decrement within the time, so we are taking d by dt of n, which is equal to lambda n. Disintegration actually proportional to n. How we have written, do you remember? See, d by dt means decrement in what? Decrement in what? N means the nucleons. First time how many nucleons are there, that much actually it is proportional to total number of nucleons. Are you with me? How we are writing? D by dt means I am representing decaying, తగ్గుతూ ఉండడాన్ని చూపెడుతున్నాను బేటా. d by dt of n, which is proportional to how many number of nucleons are there. Avoiding that proportional constant, we are introducing lambda, that's it. Okay, this is the disintegration law. Yeah, that is lambda n naught, yeah, lambda n naught e power minus lambda t. That is, we can write a naught into e power, that is a naught means what? Lambda into n naught. Okay, lambda into n naught, I am replacing a naught. A naught, which is e power minus lambda t. That is a is equal to a naught e power minus lambda t. Okay, or we can write r equal to r naught e power lambda t, where r naught, a naught, whatever it may be, we are taking, which is the rate of decay at t is equal 0. Okay, yeah, now come to n by nt, n naught by nt, we are writing e power lambda t log e n naught by nt is equal to, I am applying both side log with base e for equation n naught by nt, that is actually we know beta n naught equal to nt into e power lambda t, we have equation, no? What I am doing here, I am applying, I am taking that n naught here, n naught by nt is equal to e power lambda t. Now I am applying logarithm on both side. Okay, when you are applying logarithm on both side, then log n naught by nt, which is equal to that log and exponential mutually cancels, then lambda t left over. Okay, then I am, see, log e, log base e is there, no? To convert log base e to the log 10, base 10, what we can write? 2 point, we have to multiply with 2.303. Okay, so I'm applying that, and I'm writing 2.303 log base 10, which is n naught by nt, which is equal to lambda t. Okay, so you can observe in options in your entrance point of view also, in terms of options you can find this equation. Okay, don't get confused. If it is log 10 base 10, it should be accompanied with 2.303. Okay, 2.303. If it is not, it should be log e base e. Okay, if lambda is equal to 1 by t, yeah, nt equal to n naught by e, lambda equal to 1 by t, see here, try to understand the concept here. Lambda equal to 1 by t, nt equal to n naught by e. See, what is the meaning of this? Give me the theoretical meaning for this equation. Yes, decay constant lambda is defined as the reciprocal of the time in which the number of nuclei left 1 by e times of the number of nuclei at t is equal to 0. Is it clear? Is it clear, beta? What I am saying? Decay constant lambda, to define decay constant, what is decay constant means? It is defined as the reciprocal of the time. It is defined reciprocal of time in which the number of nuclei left is 1 by e times the number of nuclei at t equal to 0. This is actually nt by n naught, which is equal to 1 by, yeah, 1 by 2 power t by t, where capital T is half life period. What do you mean by half life period? Any radioactive element taking infinite time to disappear completely. See, as the alpha rays, beta rays, gamma rays are emitting from the unstable nuclei, the emission we are saying it as a radioactivity. So as keep on emitting, it has to be decrease its original strength, no? After t time, t1 time, t2 time, t3 time, tn times you are taking, then keep on decreasing, no? So how much time it takes? Infinite time to disappear completely, no doubt. But so it is useful too. So infinite time to disappear. So where we cannot find out the how much completely time, how much taking time to disappear. Why? Because it can disappear much time, years and years together. It disintegrates, beta. Are you with me? Years together, the some materials are there. Till now, from hundreds of years, it is getting decaying only. So that radioactive element efficiency, the radioactive element takes really infinite time to disappear completely. So we can't find sometimes. So it is necessary to find about actually half life period. We can speak about half life period. Okay, yeah, half life period we can speak. Okay, in the just after completion of these questions I will explain you half lifetime. Okay, in an exothermic reaction, the binding energies of reactants and products are E1 and E2 respectively. Then exothermic, underline that exothermic. What is the relation between E1 and E2? Question. Yeah, that is E1 less than E2. In exothermic, E1 less than E2. If it is endothermic, E1 greater than E2. Oh, that question also I have written. Yeah. In an endothermic reaction, the binding energies of reactants and products, that is E1 respectively, what's the relation? E1 greater than E2. Remember. Yeah, now come to half-life period. What is how we have to define half-life period of a radioactive element? Yeah, half-life period means individual nuclei decay takes place at random times. We cannot actually it will stipulated times. The randomness is a feature of quantum theory. That is only quantum theory feature. Okay, so the probability we can find out actually the probability of decay can given in specified in terms of half life period of the given nucleus. Whatever the nucleus we are taking, we can calculate half life period. Okay, only the probable, this is actually the probable measurement. Okay, we can take it under probability only. Okay, assume an initial number of nuclei n naught present in a sample at t is equal to 0. At a time t equal to t, half life of the nuclei will get decayed, right? Initial number of nuclei, let us suppose that n naught, beta. Okay, n naught initial number is n naught at time t equal to 0, and at time t is I'm taking time t is a half life. Okay, so now we can calculate. Yeah, just I'm drawing a graph. See, in this graph time is on x-axis, and the entire nuclei is on y-axis I have taken. So just the information I am giving. See how much time. See, at t half means what? First half life. See, first half life means for example 10 number of atoms are there. To get 5, how much the, see how much the time is required to get exactly half. Okay, are you understanding? Yeah, this expo graph is exponential graph. Okay, yeah, disintegration graph, this is decaying graph, disintegration graph, which is shows exponential relation here. Okay, n equal to n naught into e power minus lambda t, the curve shows. Okay, see, at a time, let us suppose that at a time 2t half is there. Means what? There will be n by n naught by 4 nuclei remain. Are you getting? See, first half life, it is how much the total atom remains in first half after getting first half life. If man is there, beta, he is in half lifetime. Means how many years he crossed? How many years he has to be left over? Let us suppose that man lifetime period is 100 years. Of course, if it is not, but let us suppose that it is 100 years. 50, at a half lifetime means 50 years remaining still, where 50 are crossed. Are you getting my point? Here also, whenever the radioactive material is getting disintegrate, first half life n by 2 atom remains. Are you with me? Yes. First half lifetime n by 2 atom remains. Like that, second half lifetime n by 4 remains. Third half lifetime n by 8 remains. Fourth half lifetime n by 16 remains. Yes, is it clear? Is it clear, beta? This is actually the disintegration process. Yeah, the decay curve is described by an exponential function. Yes. Yeah, half life period. See, now I am giving you definition and how to calculate the half life period we will discuss. Okay, half life period is defined as the time taken by the nuclei to disintegrate to half of its original number of nuclei. Okay, original number of nuclei to get half of its nuclei, how much time is required? That is actually half lifetime. Let us suppose that our what we can say, the man human our lifetime, entire lifetime is designed only 60 years. Let us suppose that in this 60 years actually half life period for 60 years people, half life period is 30 years. Is it for 30 years people half life period is 15 years, like that? Okay. Yeah, when t is equal to t, then see in the previous relation, that is according to radioactive decay law. Actually we have studied in previous slide. This is the radioactive law is n naught by nt is, which is equal to e power lambda t, that is log n naught by nt is equal to lambda t. That we have written 2.303 log base 10 n naught by nt, which is equal to lambda t, where lambda is equal to 1 by t. Yeah, right. Nt is equal to n naught by e. Within 1 by t time, within 1 by t time, nt will become n naught by e. Okay. So now I am substituting this. Yeah, where lambda is a decay constant. Okay. This, see, within 1 hour time, this is, see, one this is the lambda n naught, how much time we can, where lambda is a decay constant. Here n naught nt is, which is equal to n naught by e. You have to substitute this, then you can get the half life time. Yeah, I will give you end of this session, I will give you all the formulas, direct formulas. Average life period. Okay, average life period, it is defined as the ratio of total lifetime of all the n nuclei to the original nuclei. That is nt by n naught, which is equal to 1 by 2 into small t by capital, that is 1 by t, 2 power 1 by t. That is, see, that is tau, average lifetime, which is equal to tau 0 to infinity t into dn by n. dn by n, which is equal to minus lambda. 1 by n means actually minus lambda into n. Actually this is a disintegration formula, dn by dt, which is equal to minus lambda n. dn is equal to minus lambda n dt, but n is equal to n naught into e power minus lambda t, no? So dn is equal to minus lambda, within n I am writing n naught e power minus lambda t dt. Now tau is equal to 0 to infinity t. What we are doing? Are you with me? Yeah, that is dn by now t lambda n naught e power lambda t dt by n naught. Now this will be 0 to infinity lambda t e power minus lambda t dt. This is what left over. By simplifying this equation, we will get tau is equal to 1 by lambda, which is equal to T by 0.693. Okay, where, yeah, the T by 0.693, which is equal to 1.44 T. Okay, this is about actually average lifetime. Okay, average lifetime 1.44 T. Lambda is, what is lambda? Is it wavelength? That is decay constant. In case of nucleus, lambda is decay constant. Half life period T half. See, half life period T half is what is the value? Actually, one slide was missed there. The derivation of immediate to the half life period derivation. You have to write this calculate half life time. That was missed. I will add while I am posting to the blog spot. I will add that slide. Okay, one slide has missed, I think. Why the derivation, and after the derivation, you did not get the equation for the half lifetime. That is half lifetime period equation is, that is 0.693 by lambda. This is the half lifetime period equation. Okay, 0.693 by lambda. Remember this. I will add the slide. Okay, yeah. So now come to the point, decay of nucleus. That is disintegration of nucleus in terms of alpha, beta and gamma. As we said, how it is possible, we will see. Okay, first of all, come to alpha decay. Alpha particle means which is nothing but helium particle. Okay, that is emission of alpha particle by nucleus to transform into different nucleus is called alpha decay. That is alpha particle means helium particle, which is equal to helium nuclei. Okay, the difference between initial mass energy and the total mass energy of decay products is called Q of the process, or the disintegration energy. Okay, an alpha particle is composed of two protons and two neutrons. Two protons and two neutrons means that is helium nuclei only. Okay, yeah. Based on that disintegration formula, the alpha particle generally does not carry any electrons, so it has charge of 2. Okay, see, this is the alpha decay diagram. Alpha decay means here one, here the one of the nuclei. I have taken the nuclei, which is, yeah, the nuclei of radon. Okay, I have taken the nuclei of radium. Okay, so this is the radium nuclei. First of all, observe the middle one. Okay, radium nuclei, which consist of 88 protons, 138 neutrons. Means total 226, no? Radium nuclei, which is undergoing alpha decay now. See, so whenever it is undergoing nuclei here, this is the parent nuclei. In this parent nuclei, 88 protons are there, 138 neutrons are there. Whenever the radium is subjected for the radioactive decay, then what happens? By eliminating one alpha particle, alpha decay. Okay, the radioactive decay, whenever one alpha particle is getting out from it, one alpha particle means what? One equal to one helium nuclei. So one helium nuclei means here two protons and four atomic number. Two protons and two neutrons will get out. Okay, so now what will be left over? Radon. After getting two protons from the radium and two neutrons from the radium nuclei, one alpha particle, it left over with radon. Okay, the radon, which is actually consist of 86, then see, are you observing in radium 88 are there, two as left over, no? Are you with me? 2 has left over. So you have to subtract 2. Atomic number 2. So 88 minus 2, you will get 86. 226 minus 4. How much you will get? 226 minus 4, triple two you will get now. Yeah, means what here? What you are getting 88 protons here, 138 neutrons. 4 means beta 2 protons, 2 neutrons. Here what 136 neutrons will be left over, which is a daughter nuclei. Is it okay? Yeah. TK follows actually the parent nucleus, the parent nucleus disintegrates towards daughter nucleus plus alpha particle. Okay. Example of nuclear decay that produces an alpha particle. See, in the daughter nucleus and alpha particle are collectively known as decay products. Okay, the number of nucleons are conserved. The number of protons and neutrons are separately conserved. Remember this point. Now come to beta decay. Okay, emission of an electron or positron by the nucleus is called beta decay. See, alpha decay means one helium nuclei is getting out. Beta decay means one electron or one positron is getting out. That's it. Okay, remember this. In beta decay, an electron is emitted by the nucleus if beta positive beta decay is also there. In beta positive beta decay, a positron is emitting out. Okay, so beta particles are nothing but the electrons only. Remember, beta emission is going on means beta one electron is getting out. Okay, yeah, then mass number, only electron number changes, mass number doesn't changes. Remember, the general form of beta decay can be written as like this. Whenever, see, this is a parent, P means parent nuclei, ZA, what happens? Daughter nuclei gets Z plus 1, a mass number doesn't changes. Okay, why it is plus 1? One electron is emitting, that is the reason. Okay, yeah, the beta decay, a neutron transforms into proton within the nucleus according to the equation. Okay, yes, yes, n naught by nt, which is lambda t for beta decay, proton transfers into neutrons according to the equation. This decay follows like this. Okay, and gamma decay means when an excited nuclei is transmitted to the state of lower energy, it emits gamma decay. Only in gamma decay, energy only emits. There is no change in atomic number or mass number. The emission of gamma rays nucleus does not alter the either atomic number or mass number. Gamma decay produces photons. Decay follows the following pattern like this. Okay, this is the palladium. See example, palladium, there is no change in a parent and daughter, only gamma radiation emitted out. When an excited nucleus transits to a state of lower energy, it emits gamma ray, and this process is called gamma decay. And emission of electron or positron by a nucleus is called, tell me, beta decay. Yeah, now tell me, emission of helium nucleus from helium particle from a nucleus is known as alpha decay. Okay, this is what actually our, yes, this is what actually our nucleus chapter, which we have completed by today. Okay, yeah, so I will post the same to the blog spot. Okay, but you can replay the slide and you practice the equation. IPE point of view, go through the textbook once again, then you can make clear the concepts. Okay beta, okay, all the best.